Welcome, ladies and gentlemen, to another thrilling installment of Dave Does Math from Home. The topic of today's exciting lecture is exponential functions. So, without wasting any time, the first big question is, what is an exponential function? So, I want to answer this question sort of in direct contrast to the question from a couple weeks ago when we were talking about what is a polynomial. If you go back to the polynomials video for section 3.2, I opened that one up by describing polynomials as no weird stuff. One of the things I described as weird stuff is variable exponents. And that is exactly the kind of weird stuff that exponential functions refer to. A lot of people, when they try to answer this question, they think, what is an exponential function? The default place where your brain goes is a function that involves exponents. But we've been working with functions that involve exponents for weeks now. They're called polynomials. Polynomials have all kinds of exponents, but all of those exponents are constants. In polynomials, we have things like x cubed, or negative x to the 8th. When the base is a variable and the exponent is constant, that creates this polynomial thing, as long as the exponent's a whole number. If you get negative numbers or fractions, that's getting back into weird stuff. That's a different kind of function, but standard issue versions of this are polynomial with a variable base and a constant whole exponent. So, exponential functions are different because they have a constant base and a variable exponent. For reasons that I'll hopefully remember to talk about later, the base needs to be positive, but it doesn't have to be whole. It can be weird fractions if you want it to be. Like, there's no reason the base can't be 1/3 or 1/5 or whatever you want. So there's a constant positive base and a variable exponent. And this creates an exponential, well, this is an exponential expression. I guess if we want it to be an exponential function, we need a y equals. These are now exponential functions, just as these are polynomial functions. So, that's what they are. Next order of business is we need to talk about what they look like on a graph. So, the super basic introduction to your exponential function is y equals 2 to the x. And if we want a graph of this, we're going to have to make a table of values. So I'll get my x, my y values, y equals 2 to the x. We'll say x is -3, -2, -1, 0, 1, 2, and 3. These 7 numbers seem like they'll probably give me a pretty good spread of data. So I just need to figure out what happens when I raise 2 to these numbers. This one's easy. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 0 is 1. 2 to the -1 is 1/2. Negative exponents mean fractions. That's important to remember throughout this section. So this will be 1 over 2 squared, which is 1/4. This will be 1 over 2 cubed, which is 1/8. So I can make a table of values for this. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay. This is sort of the baseline number, the y-intercept, happens right here at 0, 1. To the right, I get 1, comma 2, 2, comma 4, 3, comma 8. To the left, I get negative 1, comma 1/2, 1/4, 1/8 back here. So we end up with this shape that gets really close to the x-axis on the left and really, really far away from the x-axis on the right. This is y equals 2 to the x. So, we should talk about some of the characteristics. We already mentioned that the intercept here is 0, comma 1. The really great thing about this intercept is if you change the base of this function, like if you don't want to do 2 to the x, but you really want to do 3 to the x, or 5 to the x, or 10 to the x, any number, or e to the x maybe, Euler's number, we'll talk about that in a second. It doesn't matter what you change this base to. You can change this base to anything you want. You'll always still have this as your standard issue intercept. Whatever the base is, 2, 5, 10, e, 20 million, doesn't matter. If you raise it to the 0 power, you're going to get 1. So this is sort of like your touchstone. This is always going to be a part of the basic version of any of these exponential graphs. We're going to move the graphs around in a little bit. We'll do some transformations. We'll stretch and shrink them and shift them back and forth and up and down. So this point is going to move when we do those transformations. But if there's no transformations happening to an exponential function, it always hits this point. The other thing an exponential function is always going to have, as long as it hasn't been transformed in weird ways, is a horizontal asymptote on the back end. As you move to the left here, this function looks more and more and more like the horizontal line y equals 0. So this is our horizontal asymptote. Remember that an asymptote is just a fancy word for a line that the function sometimes looks like. So we have this straight line, and on the left end of this, on the back end, the function looks a lot like this straight line. It gets real flat. So we have this horizontal asymptote at y equals 0. As you continue to get increasingly negative here, like negative 4, negative 5, negative 10 on the x-axis, you're going to get numbers that are closer and closer and closer to 0. Because you're going to be putting bigger and bigger and bigger powers of 2 into a denominator. So you'll have 1 over 16, and then 1 over 32, and then 1 over 64. And you keep on getting these fractions that are just, the numerator is always 1, and the denominator is growing and growing and growing, which means you're getting really, really, really close to 0 there on the back end. But it'll never actually touch 0, and it'll never actually cross this axis in a basic graph. Which leads me to my very next question. How can we get an exponential function to cross this axis? Let's figure it out. So I know that an exponential function is going to have a horizontal asymptote at y equals 0, and it's going to, a basic exponential function is going to get really close to that asymptote, but it's never going to touch the axis and it's never going to cross the axis. I want to figure out how we can force exponential functions to cross that axis. They won't cross the asymptote, they can't do that, but we can move the asymptote so that the rest of the graph, that flat shape on the one end and the swoopy shape on the other end, we can move the graph around so that it at least crosses the axis, and then it'll be a little more interesting. So the basic thing I want to start with is we can switch to a different base, slightly different base. We'll try 3 now. Let's try 3 to the x minus 4. I'm just going to subtract a number from this, and now we'll see what happens. When I make a table of value for these guys, I want to add an extra column. I think two of your columns should be just the basic function itself. The base function here is y equals 3 to the x. So hitting a bunch of x values and putting them as exponents on top of 3, I think should be two columns of your function. More stuff is happening here, and I'm just going to make that its own column. So whatever 3 to the x is, I'm going to subtract 4 from it over here. So this is like a multi-step process now. I'm going to make up my values for x. I want them to be negative. I'll only use 5 this time. Negative 2, negative 1, 0, 1, and 2. This is still a pretty good spread of x values. It'll give me some useful data. I'm going to put them as exponents on top of 3. So this will give me 1/9, 1/3, 1, 3, and 9. And this is just the standard exponential part of the function. And in a separate column, I will subtract 4, and then this, whatever values these are, that'll be my y. So subtracting 4 from this will give me a 5, negative 1, negative 3, negative 3 and 2/3, negative 3 and 8/9. So already with this one, we can kind of see that these values are going to get really, really close to negative 4 here. Which makes sense, because without this shift, I have y equals 3 to the x, and y equals 3 to the x has a horizontal asymptote at 0. With this shift, the asymptote is going to move 4 units down, so I should be getting numbers here that are getting really close to negative 4 instead of 0. So let me do that. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 1, 2. Okay. What do we got? 2 is at 5. 1 is at negative 1. This is at negative 3. And this is at negative 3 and 2/3. Negative 3 and 9/8. So, our intercept used to be here. The sort of the standard issue touchstone intercept I talked about used to be at 0, 1. It got moved down 4 units, which is why it's over here at 0, negative 3 instead of here at 0, 1. And the asymptote used to be at 0. It also got moved down 4 units, which is why it is here at y equals negative 4. And as promised, we have a graph cross of the x-axis. Again, doesn't cross the asymptote, but it does cross the x-axis because we moved the asymptote away from the x-axis. That'll do it for this video. There's plenty more to come. We have a bunch more transformations we need to talk about. So stay tuned.